Hello friends, welcome to Susan and John MathTube. This is the third lesson in the exam preparation series, and these videos are meant only for the students who are studying engineering in TU affiliated colleges. So let's start. So in the last two lessons we learned a lot about partial differentiation. And in lesson 2, we even learned about some of the applications of partial differentiation. And in this lesson, we will discuss something very important, that is Euler's theorem. But before we start, I want you to note a few things. I already told you these things in the first video, that is, make sure you do a very good revision with these video lessons. The second one, watch these video lessons very seriously. Always keep pen and a paper and work out the problems along with me. And make sure you note down important points and formulae. And the third one, once you complete this video, you should select some reference book which you like and work out a lot of questions. And the last and the most important, make sure you collect some past year's question papers and try to work out the problems by yourself. Okay, that's it. And let's continue. Euler's theorem. Yeah, you heard it right. I said Euler's because you're supposed to read this as Euler, not Euler. Okay, so let's go for the statement. First of all, the statement is for two variables. Okay, let u be a function in x and y. And second condition, it should be homogeneous. Homogeneous means degree will be same throughout the expression. For example, x cube plus y cube. This is a homogeneous function in two variables, because the degree is 3 throughout the expression. And one more thing, if you have an expression like x square into y, remember the degree will be 2 plus 1, that is 3. Okay, so let u be a function in x and y and let the degree be n. So we have a two variable function, a homogeneous function, and the degree is n. Then x, the partial derivative of u with respect to x, plus y times the partial derivative of u with respect to y is degree times the given function. Okay, that's a statement. It's better that you note down the statement. Now the second one, that's for three variables. So let u is equal to f of x, y, z. So we have a function in three variables, and remember it's a homogeneous function, and let's say the degree is n. Then the same thing got extended. It's the same thing which you saw in two variables, but it is a slight extension. Okay, the first thing to do is we have to analyze some homogeneous functions so that you get a clear idea about homogeneous functions. So take a look at this. U equal to x square plus y square. As I told you before, this is a homogeneous function of degree 2. Anyway, if I take this x square outside, then it simplifies to 1 plus y by x the whole square. That is, this function can be written as x to the power degree, because you can see that the degree is 2, and multiplied by a function in y by x. Look at this. If I say function in t, it means it's an expression in t. And if I say a function in y, it means an expression in y. And likewise, if I say function in y by x, it will contain terms with y by x. Okay, that is point number 1. And the next thing is, let's say u of xy equal to x square plus y square. Let's make it very clear. Now what I do is I'm going to replace x with tx and y with ty. So it simplifies to t square into the same, it's a question itself. Okay, so this is how we find the degree. But you don't need this method, you can guess the degree from here itself. But if you want to check, you can use this method. So I wanted to focus on two things. One is, given a homogeneous function, it can be written as x to the power degree and function of y by x. The second thing is, if you want the actual process to check the degree of a function, here's the method. Okay, let's go for one more function. So look at this. First of all, I'll tell you a shortcut. This is a homogeneous function. I can just take a look at this function and predict that it is homogeneous. And that is called method of inspection. Look at the first term in the numerator. The degree is 4. Look at the second term. The degree is 2 plus 2, that is 4. The third term, the degree is 4. So the degree of numerator is 4, and similarly the degree of denominator is 3. And the numerator is homogeneous, the denominator is homogeneous. So we say u is a homogeneous function of degree 4 minus 3 is equal to 1. And one more point, degree can be negative, degree can be a fraction. Okay, now let's check the things which I told you earlier. So I'm going to take x to the power 4 outside, and from denominator x cube, see, x to the power degree and then a function in y by x. So now the second one, if you don't want method of inspection, you can go for the actual process. Actual process means you replace x with tx and y with ty. Take common. Yeah, look at this. So the degree is 1. Okay, so once more I want you to take a good look at this expression. Given a homogeneous function, it can be expressed like x to the power degree and then a function of y by x. And if you want to check the degree, you can use this method or method of inspection. So in general, if this is a homogeneous function of degree n, then our u can be written as x to the power n times function of y by x. So this is very important for the proof. So let's start with the proof. Let's prove the two variable version. So do you remember the statement? If u is equal to f of xy is a homogeneous function, then we have to prove that x partial derivative with respect to x plus y times partial derivative with respect to y is equal to degree times the given function. This is exactly what we are trying to prove. Now, since this is a homogeneous function of degree n, we just learned that u can be written in the form x power n and a function of y by x. Now I have to find the partial derivative of u with respect to x. So look at this. I have x here and I have x here. So I'll be forced to apply product rule. That is, first function, what is the derivative of phi? Yeah, we will write phi dash. And one more very important thing, we are differentiating partially with respect to x. That means y is a constant. So the derivative of y by x will be minus y by x square. Those who watched the second lesson and the first lesson know why we got this expression. Okay, and plus second function into derivative of first. And then let's manipulate a little bit. I'm writing 1 2, 3, these terms here. Just rearranging, that's all. And I'm writing this over here. And I hope you remember a power m by a power n is a to the power m minus n. So we are going to apply those things, and we are finding x times partial derivative of u with respect to x. And that's it. I hope you got this. Now I'll call it equation number 2 and I'll keep it here. Okay, once more. U is equal to, this is how we started, because we learned every homogeneous function of degree n can be written in this format. Now we are going to differentiate this partially with respect to y. And now we have some good news. When you differentiate with respect to y, or partially differentiate with respect to y, x is a constant. So the whole thing is a constant. Now tell me, how do you differentiate 5 into f of x? Yeah, the derivative will be 5 times f dash of x. So I'm going to apply the same logic here. This is a constant. And then the derivative of 5 will be 5 dash into 1 by x. And now I have to multiply this throughout by y. Anyway, I applied the rule a power m by a power n is a to the power m minus n, and remember x means x power 1. Okay, now let's multiply this throughout by y, and I got this. And let's call it equation number 3. And now we have to add equation 2 and 3. So you can see that if I add them, then this and this will get cancelled. See? So I'll be left with only this. Oh, but by equation 1, this is nothing but our u. So that's it. We have proved Euler's theorem for 2 variables. Okay, now let's move ahead and let's go for some verification. So let's start with a very simple question. So look at this. Verify Euler's theorem for the function ax cube plus bx square y plus cxy square plus dy cube. So what we do first is, you can use method of inspection or the actual method, determine the degree and check whether it is homogeneous. Anyway, I like method of inspection. Yeah, the degree is 3. Of course, the degree is 2 plus 1, 3. And the degree is 3. Finally, the degree is 3. So, this is homogeneous and the degree is 3 by method of inspection. Okay, so you can use this method or method of inspection, but prove that it is homogeneous and find the degree, either by this method or this method. Now we'll write, by Euler's theorem, x into the name of the function is f. So I'm using partial derivative of f with respect to x plus y into partial derivative of f with respect to y is equal to 3 times. 3 means the degree. And now we have to verify this. Okay, I kept those things here. So the first thing we are going to find is the partial derivative of f with respect to x. And that's really easy. When you differentiate with respect to x, y will be treated as constant. So this will be a into 3x square plus b into 2x into y plus c into 1 into y square plus 0 plus differentiate with respect to y. And now let's distribute x, and you can add like terms and you get this It is obvious 3 is common, and that's it. We verified it. Okay, now let's go for a slightly different one. Okay, so the question is like, verify Euler's theorem for the function u equal to x square plus y square by x plus y. Now you tell me, what is the first thing to do in verifying Euler's theorem? Yeah, to check whether the given function is homogeneous, and by method of inspection or otherwise find the degree. Okay, I like method of inspection. So look at this, it's homogeneous, this is homogeneous. Yeah, the degree is homogeneous of degree 2, and the numerator is homogeneous of degree 2, and the denominator is homogeneous of degree 1. So the total degree is 1. Okay, so I'm keeping the question on the right side of the screen. So if you like this method, you can use this method, because this proves that the function is homogeneous and the degree is 1. But if you don't want to use this, you can use just inspection method and find the degree. It's up to you. And the next thing to do is you have to write, by Euler's theorem we get x partial derivative of u with respect to x plus y partial derivative of u with respect to y is equal to 1 into u. That 1 stands for the degree. Generally it is n into u, here it is 1 into u, and that is u, of course. So let's keep whatever we want to prove. So look at this, we want the partial derivative with respect to x and the partial derivative with respect to y. Now look at this, I told you in the last 2 lessons, the rules of differentiation and the rules of partial differentiation are the same, but your perspective should be slightly different. When we find the partial derivative with respect to x, you always treat x to be the variable. That means you will be treating y as a constant for the time being. So there it goes, denominator and the partial derivative with respect to x in the numerator, minus numerator and the partial derivative of the denominator with respect to x by denominator square. Now let's simplify, apply the distributive property here, use some symbol subtraction, and we get the partial derivative with respect to x to be this expression. No, don't say this is x minus y the whole square, because I've seen students writing like that, there's a negative here. Okay, now let's go for the partial derivative with respect to y. The same thing, but now y will be the only variable, that is, you're going to treat x as a constant. So denominator into derivative of numerator minus numerator into derivative of denominator, the whole divided by denominator square, and derivative stands for partial derivative by treating y as a variable. Okay, that's it. Now let's rearrange it, apply some distributive property and simplify. Yeah. Now I want you to take a very good look at what we are trying to prove. So let's go for the left hand side. Multiply this one by x and this by y, and I can see the common denominator, and you can apply distributive property here. Simplify. Okay, and I hope you remember a cube plus b cube. A cube plus b cube is a plus b times a square minus ab plus b square. Okay, so if you want you can apply that, but some students will like to take common here and take common here. You can do any method you like, but make sure you end up with u, the right side. That's it, we verified it. Okay, now something very important. This is from your past paper, so make sure you mark it important. And those students who are good with the proof of Euler's theorem in two variables will find this problem very easy. And before we start, let's make some things very clear. The derivative of x by 5, I mean the ordinary differentiation, with respect to x is 1 by 5. And I explained this in the last two lessons. And the derivative of 5 by x with respect to x is minus 5 by x square. My point is, if you have x by constant, the derivative will be 1 by that, and if you have constant by x, you end up with minus a by x square. Okay, now let's start. So the question is here, and so look at this. By inspection, because we learned in the beginning, every homogeneous function can be written as x power degree into a function of y by x. So u is a homogeneous function and the degree is n. So by Euler's theorem, we have x partial derivative with respect to x plus y partial derivative with respect to y is equal to n times u. Now verification time. So let's write u, and I want the partial derivative with respect to x. Remember, partial derivative with respect to x means I'll be forced to apply product rule, because I can see x here as well as here. So that's it. First function, sin something, the derivative will be cos the same thing, and x is the only variable, that means it's constant by variable, plus second function in the derivative of the first. Now look at this. Take a very good look at what we are supposed to prove. We have to multiply throughout by x. Okay, and simplify a little bit. Okay, that's it. I'll keep that here. Now again you take u, find the partial derivative with respect to y, and it's really easy because y is the variable, that means this is a constant. So you keep the constant and differentiate the function and multiply throughout by y. I'll keep it there. And once more, I wanted to take a very good look at what exactly we are trying to prove. That means we have to add them up, and which actually means we have to add these quantities, and it's clear these two will get cancelled. Oh, we got the question. Okay, that's it. So I hope you're good in this verification. So let's move ahead. Okay, now once more I'll tell you, these types of questions had been repeated many times, so make sure you work out these problems along with me. Okay, let's start. If u is equal to cos inverse x plus y the whole divided by root x plus root y, then show that x times the partial derivative with respect to x plus y times the partial derivative with respect to y is equal to minus 1 by 2 cot u. So look at this. This is very important. So look at this. U is equal to cos inverse something, and I am 100% sure you can see that the quantity inside the bracket is homogeneous, but because of this cos inverse, u is not homogeneous. I'll repeat, the quantity inside the bracket is homogeneous, but just because of the cos inverse, our function is not homogeneous. So what I do is, I'll take cos on both sides, and you might have learned in your younger classes, cos inverse will give you the identity function, so you get this. and that is exactly what I have written here. So look at this. According to Euler's theorem, if u is a homogeneous function of degree n, then I can write x partial derivative with respect to x plus y partial derivative with respect to y is equal to n times the given function. Now, if this quantity is a homogeneous function of degree n, then my Euler's expression becomes something like this: plus y times partial derivative of this quantity is equal to n times the same quantity. Now take a very good look at this. U is not homogeneous, but cos u is homogeneous, and the degree by inspection I can find it's 1 minus 1 by 2 equal to 1 by 2. So look at this. Our u is not homogeneous. This is not homogeneous, but cos u is homogeneous. So by Euler's theorem, we get x, the partial derivative of cos u with respect to x, plus y, the partial derivative of cos u with respect to y equal to half cos u. Okay, that's it. Now one more point. Remember, u is a dependent variable. U depends on x and y. And I taught you how to differentiate dependent variables in lesson 1. So the derivative of cos u will be minus sin u and the partial derivative of u with respect to x. That's it. Now I want you to take a very good look at what we are trying to prove. So let's divide throughout by sin u. Let's divide throughout by sin u. I think let's divide by minus sin u. And cos by sin is cot. So that's it. We have the answer. Okay. Now let's go for a similar problem. And this is also from your past paper questions. So if u equal to tan inverse x cube plus y cube by x minus y, then prove that this quantity. Okay, once more I'll tell you, our function is not homogeneous, but I can see that this quantity inside the circle is homogeneous. So this tan inverse character should be somehow avoided. Anyway, I'll write the question here and let's start. So look at this. I'm taking tan on both sides. So tan inverse will give me the identity function. So that's it. And by inspection, I can see that this is a homogeneous function of degree 2. Okay, now read this very carefully. Tan u is a homogeneous function of degree 2. So by Euler's theorem, we can write u plus y times the partial derivative with respect to y of tan u is equal to 2 times tan u. Okay, so look at this. Clearly, tan u is a homogeneous function of degree 3 minus 1 is equal to 2. Therefore, by Euler's theorem, yeah, that's it. That's exactly what I wrote. And I hope you remember the derivative of tan x is sec square x. So, tan u, the derivative will be sec square u into partial derivative of u with respect to x. Remember, u is a dependent variable. U depends on x and y. Okay, now take a look at what we are trying to prove. Okay, that means we are going to divide throughout by sec square x. And just make it, I hope you remember, sec theta is 1 by cos theta and tan theta is sin theta by cos theta. You can simplify a little bit. I think you remember the formula for sine 2 theta. So what's the formula for sine 2 theta? Isn't it 2 sine theta cos theta? That means 2 sine theta cos theta is, yeah. Okay, now let's go for the last question. Once more, I'll tell you this is a very important question from your past paper. So if u is equal to log of something, that is x squared plus y squared by x plus y, then prove that x partial derivative with respect to x plus y partial derivative with respect to y is equal to 1. Okay, as before, u is not a homogeneous function because of this logarithm. So we might be expecting we'll take log inverse, but there is no thing called log inverse. Log inverse in calculus is actually e to the power. So I'll put the question here and let's start. So let's imagine like this. There is no quantity called log inverse, but to make you understand, I'm going to write like this. Log inverse is e to the power. So I'm taking log inverse. Oh, sorry, there is no log inverse. That means I'm going to take e to the power on both sides. So u is not homogeneous, but e to the power u is homogeneous. So let's apply, and the degree is 1. Euler's theorem as before, and that gives you the answer. That's it. Okay, so that's it for today, but I want you to try this question. Okay, I have seen this question in the past paper, so I want you to try this by yourself now itself. Try it now itself and comment below whether you are able to solve this problem or not. So remember, u is not homogeneous, but cosec u is homogeneous, and the degree is 1 by 2 minus 1 by 3. Use the calculator. And the derivative of cosec x is minus cosec x cot x. Now I don't want to ruin your fun, so try it yourself and comment below whether you are able to solve the problem. And that's it. That's the end of lesson 3. Now, if you have any doubts regarding this topic, whatever we discussed today, please make sure you comment below. And if you're shy to comment below, just send an email. Anyway, I'll be back with the next lesson tomorrow, and that will be a very important topic, maxima minima, and it's kind of like sure 5-mark question. So till then, bye.